This video is going to be on solubility equilibria. Now, well, this is a separate topic from acid-base chemistry, really. It's usually discussed about the same time as acid-base chemistry. So, we told you a small fib in Chem 1 when we classified things strictly as soluble or insoluble. A lot of these insoluble compounds are really what we call partially soluble. In other words, they dissolve, but only to a very small extent. Okay? So a solution is said to be saturated when no further solid will dissolve. So in other words, if you're trying to dissolve up a solid and you keep adding and adding and adding, and eventually you get to the point where no more will go into solution and it starts settling out and settling in the bottom of your flask or beaker, that's when you have a saturated solution. Okay? And in a saturated solution, you have solid in equilibrium with the ions in solution. Now, we have talked about equilibrium before. You know, what an equilibrium is when you have, it's not a static frozen situation. It's where you have, simply where you have two opposing processes occurring at the same time. So let's suppose we are trying to dissolve up some solid in a beaker, let's say. Okay, so we're trying to dissolve up the solid, and we have solid, our solid is beginning to settle to the bottom of the beaker. Okay, well, once that equilibrium has been established, we still have dissolving of the solid, let's say to ions in solution, but we also have then precipitation, ions coming together and falling back out of solution and going back to a solid. So once the equilibrium has been established, you have those two processes occurring at the same time, but the concentration of ions in solution doesn't change. Okay, so it's not static frozen, it's you have the two processes occurring at the same time so that the concentration of ions doesn't change. Okay, so when your silver chloride dissociates, it gives us a silver ion and a chloride ion. So how would we write the equilibrium expression for this? Same way we did before when we talked about equilibrium. The products over reactants and the coefficients become the exponents. So it's concentration of silver ion times concentration of chloride ion divided by concentration of silver chloride. Except for the fact that silver chloride is not soluble. It's a solid that's basically fallen out of solution. You can't express the concentration of a solid. So that's basically a 1, which means then that it drops out, and your K, which we call KSP for solubility product, is simply the product of the ions. Okay. Let's look at another example here, silver carbonate. Now, the only difference is that the silver carbonate dissociates into 2 silver ions and 1 carbonate, right? Because carbonate's a 2 minus ion, silver is a plus 1, right? So in your formula, you have to have 2 silver ions to balance the charge on the carbonate. So when it dissolves up, you get 2 silver ions for every 1 carbonate. But that comes into place in 2 ways. Okay, so when it dissolves, you get twice as many silver ions as you do carbonate. And then when you write the equilibrium expression, your coefficients become the exponents. So that 2 here becomes a square here. So your solubility product constant is the concentration of silver ion squared times the concentration of carbonate. Okay, so that's basically what solubility equilibria is. So there's 2 kind of calculations I can give you. Okay, So the first is where we calculate KSP for molar solubility. So in other words, this is where I tell you if a solution is able to dissolve so many moles of a solid. Let's say what is your solubility product constant? So as an example, let's suppose that 1 liter of water is able to dissolve 7.1 times 10 to the minus 7th moles of silver bromide. And from this information, we want to calculate the KSP of silver bromide. Okay. Now, just the fact that we're given 1 liter of water makes it easy because the number of moles automatically becomes the molarity. So let's start out by writing our equilibrium expression, or our reaction rather. This is an easy example because it's a 1-to-1 solve. So your silver bromide dissolves up to give us 1 silver and 1 bromide, right? So if 7.1 times 10 to the minus 7 moles of silver bromide it dissolves, how many moles of silver ion do we have? 7.1 to the minus 7th. How many moles of bromide do we have? 7.1 to the minus 7th. And like I said, the 1 liter of water makes it easy because the number of moles automatically becomes the molarity. So your KSP is the product of the ions. So basically 7.1 to the minus 7th times 7.1 to the minus 7th. That's 5 times 10 to the minus 13th. Okay? Look at a second example. Now we're going to talk about lead fluoride. Now, it's not a 1-to-1 solve, so it's going to complicate things a little bit. So let's say that 1 liter of water is able to dissolve 2.1 times 10 to the minus 3rd moles of lead fluoride at 25 Celsius. We want to calculate solubility product constant of lead fluoride. So let's write our reaction. When the lead fluoride dissociates or dissolves up, it's going to give us 1 lead ion and 2 fluoride ions. Okay? But your coefficients become your exponents, so your KSP is the concentration of lead ion times the concentration of fluoride squared. Okay? So if you're able to dissolve 2.1 times 10 to the minus 3rd moles of lead fluoride, what's going to be your concentration of lead ion? 2.1 times 10 to the minus 3rd. What's going to be your concentration of fluoride? 4.2 times 10 to the minus 3rd. That's this number times 2, right? But then we not only have to multiply it by 2, we have to square it because the coefficients become the exponents. In other words, this 2 becomes a square here. So not only when we figure out the KSP, not only do we have to double this, we also have to square it. And this comes out to be 3.7 times 10 to the minus 8. Okay? Now, let's take a look at a second type of problem that I can give you, which is probably a little bit more difficult. And it's calculation of the molar solubility from KSP. So in other words, I give you a KSP and say, all right, what's going to be the concentration of a saturated solution, or how much of this solid can dissolve? So we'll work the reverse of the problem on the previous slides. So suppose we look up the KSP of silver bromide. We find it to be 5.0 times 10 to the minus 13th. What's the molar solubility of silver bromide? In other words, what would be the concentration of the ions in a saturated solution? Or how much of the solid will dissolve? It amounts to the same thing, because this is a 1-to-1 solve. So your silver bromide dissociates into 1 silver ion and 1 bromide, right? So we'll let X represent the extent to which the solid dissolves. It's 1-to-1, right? So if X moles of this dissolves, we'll have X moles of silver ion and X moles of bromide ion. So these two will each be equal to one another, which will be X. So your KSP is simply the product of the ions, right? So the equation that you'll have to solve well to do is set that equal to the KSP. So in other words, the equation you'll have to solve is x squared is equal to KSP. Remember, in a saturated solution, the product of the ions is equal to the KSP. Solve this for x. You simply take the square root of the KSP, and this comes out to be 7.1 times 10 to the minus 7th. Okay, so for any 1-to-1 salt, like the silver bromide that we worked here, or let's say magnesium carbonate or lead chromate, any 1-to-1 salt, the equation that you'll have to solve comes down to x squared is equal to the KSP. So basically, take the square root of the KSP. Now, one last part of this problem, how many grams of the silver bromide would dissolve in a liter of water? This is just a moles to grams conversion. So we figure out the molar mass of silver bromide. That's 107.9 for the silver, plus 79.9 for the bromine. That's 187.8. Multiply that by 7.1 to the minus 7th, and you get 1.3 to the minus 4th. Now, one of the reasons I did this is I wanted to demonstrate what a small number this really is. You would not be able to measure this on on the balances that we have in the general chem lab. They only go to 3 places past the decimal. You would have to have a special balance to be able to get more than 3 places past the decimal to even be able to measure a mass this small. Point is that the compound dissolves, but it dissolves to a very, very, very small extent. All right. Now, let's work a second example. Okay, and now we'll do one for salt that's not 1-to-1. Okay, so if the solubility product constant of silver carbonate is 8.1 times 10 to the minus 12, we want to calculate the molar solubility of silver carbonate. In other words, how much silver carbonate will dissolve in a liter of water, or what will be the concentration of of the ions in a saturated solution. So we'll let X represent the extent to which the solid dissolves, right? So if X moles of this dissolve up. Remember, this is not, this is a 2-to-1. It's not a 1-to-1 salt. It's a 2-to-1, okay? So we'll get, if X moles of the silver carbonate dissolves, we'll get 2X moles of the silver and X moles carbonate. But then we have to square the silver because your coefficients become exponents. In other words, your KSP is concentration of silver ion squared times concentration of the carbonate. And we said if X moles of this dissolve, we'll get 2X moles of the silver, right? So so let 2X be the concentration of silver ion. We have to square that. And one more time, that's because your coefficients become your exponents. And we'll let X represent carbonate. So basically 2X times 2X is 4X squared times X is 4X cubed. So the equation that you have to solve comes down to 4X cubed is equal to the KSP. So you basically divide it by 4 and take the cube root, and you get 1.3 times 10 to the minus 4th. Now the way I did that, your calculator may be somewhat different, but the way I do that here is you take the KSP, 8.1, let me reset this, we take 8.1 to the minus 12th, okay, then we divide that by 4, okay, so to take the cube root, we use the inverse function of the y to the x power. That's the cube root. So inverse y to the x, or cube root of 3. And you get 1.26 times 10 to the minus 4th, which I rounded up to 1.3 because we only had 2 significant figures in the KSP. Okay. So how many grams of silver carbonate would dissolve up in 1 liter of water? So we figure out the mass of silver carbonate, mass of 2 silvers, 2 silver atoms plus the mass of a carbon atom plus the mass of 3 oxygen atoms comes out to be 275.7. That's pretty heavy. You multiply by the 1.3 to the minus 4th, and this comes out to be 0.036 grams. Okay. So there's a couple of more things we need to talk about here. Next is a common ion effect, okay, which is important. So the solubility of a salt is lowered in a solution that contains an ion in common with the salt. So suppose, for example, I ask you what's the molar solubility of silver iodide. If we look it up, we find that KSP of silver iodide is 8.3 to the minus 17th. Okay? So to get the molar solubility, we simply take the square root of the KSP, and you get 9.11 times 10 to the minus 9, right? So that's really insoluble. It's even more insoluble than the silver bromide example that we used. Okay. So the second part of this problem is, suppose I ask you, what's the molar solubility of silver iodide in 2/10 molar sodium iodide? Now, you see the problem. We're trying to, well, first of all, let's think about this now. Sodium iodide is soluble. That's soluble. So the sodium iodide is going to dissolve up into sodium ion plus iodide. So what we're really saying here is the concentration of iodide is 0.2 molar. Okay. But this KSP, that KSP is the product of the ions. In other words, what we're saying is, when we say that the KSP is 8.3 to the minus 7, what we're saying is that in a saturated solution, then the product of those ions is going to be equal to 8.3 times 10 to the minus 17. This cannot be exceeded. So if we're trying to dissolve this up in a solution that already has 0.2 molar iodide, in other words, if this is starting at 0.2, this is going to be much lower. In other words, we're limiting, this is what we call it, the common ion. In other words, iodide is common to both compounds, sodium iodide and silver iodide. We will limit how much of this can dissolve because the product of these ions cannot exceed the KSP. So if X moles of your silver iodide dissolve, we'll have X moles of silver ion, and we'll have 0.20 plus X moles of iodine. Where are we getting this from? Okay. Well, the 0.2 is coming from the sodium iodide, and the X is coming from the dissolving of the silver iodide. And we're going to neglect the iodide from the silver iodide. And we're going to assume that 0.20 plus X is for all practical purposes equal to 0.2. Okay, so we know the product of our ions of silver ion times iodide is 8.3 to the minus 17, but we're assuming that the iodide is 0.2 from the sodium iodide. So simply solve this for silver, so 8.3 to the minus 17th divided by 0.2, and you get 4.2 to the minus 16th. Okay, so we change the solubility a lot, by 7 orders of magnitude, from 9.11 times 10 to the minus 9 down to 4.2 to the minus 16. Because one more time, product of these ions cannot be exceeded. And if you're starting out with a solution that already contains one of those ions, then you're going to limit the solubility. And that's basically common ion effect in a nutshell. So let's work one more example here. A second example of the common ion effect. And let's talk about magnesium hydroxide. Okay, magnesium hydroxide has a KSP of 8.9 times 10 to the minus 9. So let's first calculate the molar solubility of magnesium hydroxide. Right. So that's going to dissociate. That's going to dissociate to give us 1 magnesium ion plus 2 hydroxides. Okay, so if we'll let X represent the moles of this to dissociate, we'll get X moles of magnesium and 2X moles 2X moles of hydroxide. So X times 2X, and we have to square the 2X is equal to the KSP, so 4X cubed is equal to the KSP, divide by 4, take the cube root, and you get 1.3 times 10 to the minus 4. So, second part of the problem is, what is the molar solubility of magnesium hydroxide in 10th molar sodium hydroxide, right? So this is a common ion effect. Now the common ion is hydroxide. Okay, so we're trying to dissolve magnesium hydroxide in a solution that already has hydroxide. Okay, so this is a strong base. That's 100% dissociated. So what we're saying is that that our concentration of hydroxide is 0.1. So if X moles dissociate, or dissolve rather, our concentration of magnesium will be X, and our concentration of hydroxide will be 0.10 plus 2X, right? Now, the 0.1 from the sodium hydroxide and the 2X from the magnesium hydroxide, right? Because if X moles dissolve, we'll get X moles of magnesium and 2X moles of hydroxide. So X times 0.1 squared is equal to the KSP, which is 8.9 times 10 to the minus 12, and it comes down, you divide by 0.1 squared, you're basically just moving the decimal place over, and you get 8.9 times 10 to the minus 10. So we reduced the solubility by what? Roughly 6 orders of magnitude, from 1.3 to the minus 4 to 8.9 times 10 to the minus 10. Okay, so we got one last thing to talk about here, and that is predicting the formation of a precipitate. Now, like I was saying previously, solubility product cannot be exceeded. Okay, it cannot be exceeded. Okay, if the product of the ions is greater than the KSP, that's a situation that really can't happen. So in other words, a precipitate would be produced and the ions would start coming together and falling out of solution until the concentration drops and becomes equal to the KSP. So as an example, let's use calcium sulfate. Okay, KSP of calcium sulfate is 2.4 to the minus fifth. Right, so one more time then, your KSP in this case is the product of the ions. In this case, it's going to be concentration of calcium ion times concentration of sulfate ion. Now, one more time, that cannot be exceeded. This cannot exceed 2.4 to the minus fifth. Okay? So let's suppose we mix together 0.0025 molar calcium chloride and 0.0025 molar sodium sulfate. Now, don't get confused by the chloride and the sodium. Those are just spectator ions. Okay, the chloride is a counter ion for the calcium, and the sodium is a counter ion for the sulfate. Sulfate is charged. You can't add sulfate by itself. You have to add a compound of sulfate. Okay, but your products of your reaction would be the calcium sulfate and the sodium chloride. Sodium chloride is obviously soluble, so those are just spectator ions. So in other words, what we're saying is concentration of calcium ion is 0.0025 molar and concentration of sodium ion is 0.0025 molar. Well, your KSP, or equilibrium expression, is the product of the ions. So that is, product of the ions is 6.2 to the minus sixth. Now, if the product of the ions is less than the KSP, like it is here, no precipitate is produced. So we're not yet at the point where we're equal to the KSP. Solution is not saturated. In other words, nothing's going to happen. Okay. Now let's suppose we go to a solution that is 0.0096 molar calcium chloride and 0.0025 molar sodium sulfate. And you multiply those two together and you get 2.4 times 10 to the minus fifth. Okay? Well, now we're equal to the KSP. In other words, the product of the ions is equal to the KSP. So the solution, at this point, the solution is saturated. It doesn't necessarily mean we're going to have a precipitate, but we're at the point, though, where the solution is saturated. That's the maximum concentration that you can have. So if either of these concentrations were bigger than this, then we would get a precipitate, because the product of the ions would be bigger than the KSP, which is not possible. Which means the ions would start coming out of product would start coming out of solid would start coming out of solution. So let's say I didn't work a third example here, but let's suppose this were 0.0096 and this were 0.0096, right? Well, if you make this bigger, anything bigger than 0.0025, this will be bigger than the product. The ions will be bigger than the KSP. In other words, so if each were 0.0096, then we'd have a number that was bigger than the KSP and the solution, and we would start getting a precipitate. In other words, calcium sulfate would start coming out. So one more time. If the product of the ions is less than the KSP, nothing will happen. No precipitate. If the product of the ions is equal to the KSP, the solution is saturated. And if the product of the ions is bigger than the KSP, you'll get a precipitate when the solutions are mixed. And that's it for solubility equilibria. We will stop here.